Welcome to The Explainer. Today, we are peeling back the curtain on the massive, complex, and let's be honest, absolutely fascinating systems that power the generative AI you use every single day. Okay, so let's just dive right in. It seems so simple, doesn't it? You type a prompt, you hit enter, and a moment later, this coherent, often amazing answer just appears. But that journey, the one your prompt takes from your screen and back again, it is an incredible feat of engineering. Yeah, it is so much more than you think. This isn't just one giant digital brain whirring away somewhere. No, it's a whole ecosystem of different components, all working in concert. And in this explainer, we're going to explore that hidden architecture, an architecture of trust that works behind the scenes to give you a safe, accurate, and helpful answer. So this specialized world has a name, LLMOps. That stands for Large Language Model Operations. It's a whole field built specifically to handle the unique challenges of models with billions, and I mean billions of parameters. You can think of those parameters as all the individual little knobs and dials the AI uses to store its knowledge and make decisions. LLMOps, well, that's the industrial scale plumbing and the power grid for all of this AI. So, what's the first huge problem that LLMOps has to solve? Well, standard AI models, they have a knowledge cutoff, right? They only know what they were trained on up to a certain point in time. And they can also just make things up. You've probably heard of this. It's a phenomenon we call hallucination. So how do you fix that? How do you give an AI an open book exam instead of a closed book one? Well, that is where this brilliant technique called retrieval augmented generation, or RAG, comes in. It's a super clever way to separate the AI's ability to reason from its static, frozen-in-time knowledge base. Okay, so this slide breaks down the magic into 4 key steps. But here's the core idea. Your question is used to look up relevant information before the AI even tries to come up with an answer. The system literally finds the right pages in its library, hands them to the AI, and says, here, use only this to answer the question. And that's exactly why a modern chatbot can tell you about what happened in the news last night instead of just saying, sorry, my knowledge ends in 2023. It just dramatically cuts down on those weird, made-up answers. All right, on to the next challenge, and this one is about sheer, mind-boggling size. These models, they are gigantic. They contain billions of parameters, and that makes them incredibly expensive and pretty slow to run. Just look at that number, 280 gigabytes for a single large model. That is far, far more memory than what's available on even the most high-end computers you can buy. So how on earth do you make this practical? Well, the solution is a really clever technique called quantization. And the analogy on the slide here is perfect. It really is like compressing a beautiful, high-resolution photo into a smaller JPEG. You lose a tiny, tiny bit of detail that you can't even perceive, but you get a massive reduction in the file size. For an AI, this means reducing the numerical precision of its weights, basically going from super detailed 32-bit numbers down to simpler, much more efficient 8-bit ones. And this chart, wow, it really brings that to life. Just look at the difference. The original model, using 32-bit precision, that's 4 bytes for every single parameter, that's our baseline at 100%. But by quantizing it down to 8-bit integers, just 1 byte per parameter, the memory requirement absolutely plummets to just 27% of the original. That is a nearly 4 times reduction in size. It's an absolute game changer for getting these powerful models to run on more accessible hardware. But look, making a model smaller and faster, that's only part of the story. A powerful, optimized model isn't actually useful if it's not fair or if it's not safe. So the next huge challenge for LLMOps is building in the necessary ethical guardrails to manage really tough problems like bias and privacy. You know, one of the toughest challenges is dealing with bias that's just baked right into the training data itself. And the first type to really get your head around is historical bias. This one's tricky for engineers because the data isn't technically wrong. It's just accurately reflecting a world with all of its historical inequalities. The model simply learns the patterns it's shown, so if that data reflects bias from the past, you better believe the model will too. And then there's representation bias. This happens when the data collection process itself is just flawed, and it leads to a data set that doesn't really reflect the real world. You know, as the slide says, if your early image data sets mostly have pictures from Western countries, the model is naturally going to be worse at identifying things in images from everywhere else. It's the classic garbage in, garbage out problem. And a third kind is measurement bias. Now, this one is subtle, but it is so critical. It happens when developers use a proxy, basically a stand-in for what they really want to measure, and that proxy is flawed. Using arrest rates to represent crime rates is a textbook example because it forces the model to learn all the biases that are inherent in policing patterns, not the actual real distribution of crime. So tackling bias is one part of the safety puzzle. Privacy is the other huge piece. And here, one of the most powerful techniques is something called differential privacy. Think of it like this. Imagine you want to find the average age of everyone in a room, but without anyone having to reveal their actual age. What if you had everyone add a small, random number, say between -5 and +5, to their real age before they report it? The final average is still going to be almost perfectly correct, but it becomes mathematically impossible to reverse engineer any single person's real age from that data. That's the core idea here. It's brilliant. Now, something that is absolutely essential to understand is that an AI model isn't just a big file of data, it is executable code. And just like any other program you run on your computer, its supply chain has to be secured from the ground up. This gets right to the heart of the risk. Seriously, some of the standard file formats for saving models can actually contain malicious executable code. So if you just download and load an untrusted model from somewhere on the internet, you could be opening the door for an attacker to get into your system. So the solution that the community has really rallied around is a new secure format called Safe Tensors. It is designed from the ground up to only contain the model's data, the weights and nothing else, which completely prevents this kind of attack vector. But how do you actually know that the model you're using is authentic, that it really came from a trusted source? Well, that is where cryptographic signing comes in. It is basically a digital tamper-proof seal. It guarantees that the model hasn't been altered one bit since it was created by its developer. And the final layer of this fortress is about controlling access, and it uses a classic security idea, the principle of least privilege. You can see it in action in the examples here. A data scientist, sure, they get read access to the data, but they can't just write to the live production system. It means people and programs only get the exact permissions they need to do their jobs, and absolutely nothing more. So there you have it, from grounding models in reality with RAG, to shrinking them with quantization, to building in all these safety and security guardrails. This is the hidden world that actually makes AI work for all of us. The real question is, as these AI systems become exponentially more powerful, can this architecture of trust actually keep pace?